Hello, everybody. My name is Atapoor, and the title of our paper is The Cost of IEEE Arithmetic in Secure Computation. This is a joint work with Dr. David Archer and Professor Nigel Smart, and you can find the full version of our paper in this link. Let's have a short overview on the content of the presentation. I will start by some background about multi-party computation and Mode 2 and Mode P words. And at the end, I will talk about our contribution and the conversion algorithms that we propose. And we'll finish by showing some graphs which shows the performance of our algorithms. MPC stands for multi-party computation. There are several parties vying to evaluate a function with their secret inputs, and the requirements of these protocols are security and integrity of computation should be held, and the parties should not learn anything about the other parties' inputs. And the only thing that they can learn is the correct output. There are two types of circuits, binary circuits and arithmetic circuits. Binary circuits are based Mode 2, and there are some logic gates like AND, OR, NOT, and NAND inside them. And they take a fixed number of bits as inputs and output a single bit. Arithmetic circuits are based Mode P, and they use for computing polynomials. They take variables or numbers as inputs. For special purpose functions, like in MPC, we need to mask or open some values. In those kind of cases, they are not really arithmetic circuits. We are not really using these kind of circuits, but something similar. Let's move to Mode 2 world. Computers cannot store all the real numbers. For example, between these two real numbers, there are tons of other real numbers. So it is not possible for computer to store all of them. And this is a problem. And the solution to that is create a format of storing for floating point. And the accepted standard for floating points are different types of IEEE 754 representation. In this kind of representation, beside numbers, they define finite numbers, infinities, not a number values, and exceptions, which we'll talk in next few slides, and error handling. And they are error handling. They are not perfect, but they are very, very good because they are rounding numbers to the nearest number. And in this way, they can, by losing a little bit of precision, they can store a lot of numbers, small and big numbers. Here are three different types of IEEE 754 floating point standard. They differ, basically they differ in their sizes. For example, for single precision float, we have 32 bits, double precision has 64 bits, and extended precision float has 80 bits. And we are using double precision in our paper. In this representation, we have a single bit of sign, which if it is 1, shows number is negative. If it is 0, shows number is positive. And it follows by 11 bits of exponent. And at the end, we have 52 bits of mantissa. Here are the exceptions that I mentioned. If we have all zeros for exponent and mantissas, then it means it is 0. Based on the sign bit, it is positive or negative 0. But if we have all ones for exponent, we have two cases. Either all the mantissas are 0, which shows positive or negative infinity based on the sign bit, or we have something else for mantissa, which shows it returns none, which means there is an error happening somewhere. For our papers, we needed to generate a circuit, which we needed to generate a combinational circuit, which needed to optimize it with and depth, and use a open source Berkeley software library, using a compiler of CBMC.GC, we give a C code to this compiler and get the optimized circuit. CBMC.GC compiler converts a software function written in C to circuit, which is suitable for MPC, which is MPC friendly. And it proceeds in 3 steps. In first step, it unrolls loops in the source algorithm, next converts the algorithm to a single assignment forms. Finally, it decreases the depth of AND gates, and it optimizes it. Here in this link, you can find the circuits that we generated, and I just put 2 functions of addition and multiplications here. For example, if we want to add 2 floating point to in this kind of word, in this mode 2 word, to add 2 floating points, we need something about 5,000 AND gates, 8,000 XOR gates, and 2,000 inverse gates, and the depth is 235. So we are using a huge number of logic gates just to compute a function of addition and multiplication. Okay, let's move to mod T word. In this word, we are using we are using the representation given by Ali Asghari et al. In 2013. They have the sign bit, Monty sign, exponent, same as mod 2 word, but they define 2 more flags of 0 and error. And if 0 flag is 1, which means number is 0. If 0 flag is 0, which means number is non-zero. And when error flag is 0, which means we do not have any error in our computation. But if it is non-zero, which means we have error. And here is the representation. Arithmetic is complex. Addition is really complex. For example, to add these 2 numbers written in the representation of Ali Asghari et al., proposed by Ali Asghari et al., we can see that base are the same, but still to add these 2 numbers, we need to shift the second number, get the same exponent, and then we can add them together and get the final result. Here is in more detail. And note that these shiftings that I mentioned here, that we need to shift the second number and get the same exponent, this shifting needs to be done in secret, which is costly. But multiplication is simpler. To multiply 2 numbers in this representation, we just multiply Monty cells together, and then we have the same base, and we just need to add the exponent and get the final result. Here is in more detail, explained in more detail. Here are 2 graphs for addition in mode 2 word and mode P word. Y-axis shows the time in second, and X-axis shows a number of party N, and T threshold, which is threshold. And I should mention that we are using Shamir access structure here. You can see that I explained that addition is complex in arithmetic circuits in mode P words. But still, as you remember, if you remember, in mode 2 words, I explained that to add two floating points together, we need lots of something about 5,000 AND gates and 8,000 XOR gates and something about 2,000 inverse gates do this addition in mode 2 words. So we can see that still in arithmetic circuits, we are far better than binary circuits, I mean mode 2 words. So this motivated us to give a conversion to construct a current conversion which can convert from this word to mode P word and to the other representation. And here is multiplication, and the same. We have y-axis shows second, and x-axis shows number of parties and threshold, and and the access structure is Shamir access structure, but in the paper we have full threshold access structure as well. And here you can see that still arithmetic circuits are better than binary circuits doing a multiplication. Let's see our contribution. As I mentioned, addition and multiplications are cheap in mode P words compared to mode 2 words, but comparison and most significant with extraction and truncation are cheap in mode 2 word compared to mode P word. And IEEE error analysis is well understood in mode 2 word. I mean, errors are completely defined in mode 2 word, but in mode P word, this kind of analysis is non-standard. We are using a key idea here. Our key idea is DOBIT, which stands for double authenticated bits, and I will explain it in the next slide. We want to convert a value which is represented in mode 2 to a value which is represented in mode P. I'm not going through the algorithm in more detail, just we had lots of challenges because to converting between these two words, we needed to, as I mentioned in IEEE representation, we have sign, exponent, and mantissa. But in mode P representation, we have two more flags of Z and error, and we needed to define them here. And here you can see some converts. In each of them, we need to convert them, and we are using DOBITs. If I want to explain about DOBITs, I would say that DOBIT generates two random bits in two modes, mode 2 and mode P. We first mask our secret value with when we put a value in the bracket, which means they are secret. When we want to first we mask our value with the random generated in the same mode, and then open it, then this V will not reveal anything about our secret input. Then by the other, using the other random which generated by DOBIT in mode P, we cancel out the effect of this R2 that we added, and we get the value in mode P. And we have another conversion algorithm to convert from mode P words to mode 2 words for another purpose, like comparisons and other things that I mentioned. Here are the performance of our algorithms. Again, I put the graphs of Shamir access structure, and here are time in second, and here are a number of parties and threshold that we have. And you can see that this is a cost that we pay to convert from mode 2 word to mode P word. For example, for addition and multiplication, still paying this cost, still it gives us the better result than doing addition and multiplication in mod p word. So we when we want to add or multiply floating points together, we can use this compiler, and we can do our computation faster in mod p words. And here is the vice versa. I mean, converting from mod p to mod 2 word. To sum up, I would say that MPC can take use of both arithmetic and binary circuits using the algorithm that we proposed in this paper, the conversion algorithms that we proposed in this paper. And I mentioned that we needed, for efficiency reasons, we needed to generate an MPC-friendly circuits which has low and depth. And for future direction, one can try our algorithm with extended doubly authenticated bits. I mean, instead of using doubles, we are using doubles because we are implementing our work in a scale MAMBA, which we have doubles there. But one can try our algorithm with extended doubly, E-doubles, proposed by Escudero et al. In Crypto 2020. And basically, in doubles, doubles generates 2 random bits, but E-doubles generates a set of random bits in both mod 2 and mod p. So it would be very nice to see the result of our algorithm using this E-doubles. And even further, we can try our algorithm with faulty doubles given by Bohm et al. In 2021. Basically, they modified this E-doubles because these E-doubles are kind of optimized for using in MPC protocols, but these guys with using faulty doubles, which is a modified version of E-doubles, they are using these kind of faulty doubles in zero knowledge proofs. Thank you very much.